All right, this problem has two parts, so we'll start with the first part, but they're both going to use the same picture, and that's definitely the first step. So the first thing we see is we have an oil well that is located in the ocean 9,000 feet from the coast. So let's draw the coastline. So we'll call this the coast. And then all this out here is the ocean. Okay, so what we have is we have our oil well that's right here. And nice straight line, Mr. Howard. That's 9,000 feet. Okay, so I'm actually going to move that over here, 9,000 feet. Okay, the oil refinery is located 13,000 feet down coast from the well. So if this is the well, 13,000 feet down coast is going to be down here. So here's the refinery. Okay, so and we know that this distance is 13,000 feet. Okay, so the question becomes, it's a cost question. So we have $18 per foot on land or on water, and then $8 per foot on land. So we want to figure out the best combination of the pipe in the water and the pipe in the land. And we're not sure how far down coast we should hit to make the best cost. So we're just going to pick some random point and say we're going to hit X points down the coast. X feet down the coast, okay? So then if this is X and the whole thing is 13,000, then our distance on land ends up becoming 13,000 minus X. Then we have to figure out what is our distance on water, because we're trying to figure out a cost equation. So we need to represent the distance on water somehow, and we're going to do so using the Pythagorean theorem. X squared plus 9,000 squared equals this distance squared. So if we take the square root of that, it's going to be x squared plus 9,000 squared. So square root of that. So it's square root x squared plus 9,000 squared. And that just comes from the Pythagorean theorem. Okay? X squared plus 9,000 squared equals this whole thing squared. So if we take the square root, it's going to be the square root of x squared plus 9,000 squared. So now let's create a cost equation, which I'll just put up here. So my cost, we'll call it C of x, just because it's cost, equals, okay, $18 times our distance on water, which is x squared plus 9,000 squared, plus, okay, what's our cost on land? It's 8 times our distance on land, which is 13,000 minus x. So this is our equation that we can graph, so let's do that now. Plug it into Desmos. So here's what I get when I'm graphing. I get 4,465.25 and then 249,120.639. So that means, okay, this is x, so that means that we are striking the ground. Didn't mean to circle that whole thing, just this. We're striking the coast 4,465.25 feet down coast from the oil well. And then the minimum cost then ends up being $249,120 and about 64 cents. That is the minimum cost of the job. And that's a pretty expensive job. And if we strike the coast any further, it's going to start to become more expensive, right? Even just right here, we're up in the 300,000 range. So that's a pretty expensive job for sure. But this is the minimum possible cost of the job, and we know that we just need to strike the coast X feet down. So part 2 of the problem, we're dealing with the same picture, but it's going to be a little bit different because this is a person trying to get from the oil well to the refinery. So he doesn't have to necessarily follow the same path as the piping does. So the thing is, let's talk about units for a second. So when we made our cost equation, we had C of x equals 18 represents dollars per foot times square root x squared plus 9,000 squared. Okay, that's a very messy 9,000. Oh my gosh, 9,000 squared. Okay, and this represents feet. So this portion represents feet in water. This represents dollars per feet. So these units are going to cancel, and we're just left with dollars, which is what we wanted. We wanted the minimum cost of the job, cost being units in dollars, okay? So doing the equation this way is going to lead to an overall ending of dollars. But when we're talking about speed, if we're saying that he moves in a kayak 880 feet per minute and rides a bike 15,000 feet per minute, we want to end with the minimum time, the fastest possible time, which means we need to flip our 880 because we want to end up with a final units of minutes. So let's see what happens. We're going to use the same equation, just substitute in some different stuff. So let's try in 1 minute, he can travel 880 feet. We're going to multiply that by square root x squared plus 9,000 squared, which is feet. Okay, plus he travels in 1 minute, he travels 1,500 feet. And we're going to multiply that by our 13,000 minus x. Okay. So let's see what happens. What happens with our units? Feet is going to cancel with feet, just like it would have over here if we had written our units. Feet would have canceled with feet down here. And we're just left with minutes, which is what we want from this equation. Okay, so we'll call this like t of x for a time. Okay. So this is what we want to plug into Desmos, and we want to use it to minimize his time on the water. The thing that sucks is we get a straight line, or it looks like a straight line because this is such a big scale for our graph, so it doesn't look good. But the thing that's sweet about Desmos is it highlights key points. So if we zoom in on this, see how we have this gray point right here? That must be a key point of the graph. So if we go back to Desmos and click on that gray point, that's going to be the minimum. So let's go back and look at it. Okay, so now I have my graph again, but this time I've clicked on that point that Desmos highlighted. And look, okay, it says when we strike the coast, 6,519 feet, 0.9 roughly, down coast, it's going to take him a minimum time of, well, about 17 minutes. So if let's go back to our picture. If he strikes down coast at 6,519 feet, it's going to take him a minimum time to get there of 16.949 minutes. So that's his fastest time that he can get from the well to the refinery using a kayak and a bike.